our Beyond Cellular Green Generation project, we have determined that the use of small cells, along with the separation of signaling and data functions of the cellular networks, can dramatically improve energy efficiency. When combined with low-power hardware and efficient backhauling technologies, our research has shown that this approach can achieve an energy efficiency for dense urban areas that is more than 8,000 times higher than that of the first LTE deployments in 2010. This dramatic finding represents one of the most significant contributions toward the Green Touch goal of increasing energy efficiency by a factor of 1,000. Here is how we came up with this thesis. Traditional wireless access network architectures are founded on the concept of cellular layout, which provides full coverage in the service area anywhere at any time using a set of base stations. To ensure this continuous network accessibility, the network today remains active regardless of how many users are present and how much traffic they generate, wasting a lot of energy. Base stations cannot be switched off without causing connectivity issues to users that need to exchange data with the network. I like to make a parallel comparison with lighting. At home, we can save energy just turning off the light when we leave a room. However, public lighting systems must always remain active, even if there is no one in the street to ensure a safe and always accessible urban environment. Traditional mobile networks are like public lighting systems, and their energy consumption can only be partially adapted to traffic load. To maximize energy efficiency, we need to have an energy consumption that is proportional to the actual load, consuming energy only when necessary to transmit data. Unlike traditional architecture, our BCG2 project uses small cells and completely separates the signaling and data functions at the wireless interface. With their reduced distance between network and user terminals, these small cells will consume less energy than traditional macro cells. However, we will need much more of them, and therefore, at any given time, many of them will be inactive. So by separating the signaling and data functions, they can be turned off and on when needed, making the energy consumption proportional to traffic load and the energy efficiency extremely high. A separate infrastructure for signaling provides continuous network accessibility with full coverage so that communication services can be requested at any time by users. Signaling data rates are normally much lower than user data rates, so the signaling infrastructure can be designed for this, resulting in greater energy efficiencies.
To show the potentials of the BCG2 architecture, we developed a demo that emulates some of the key components of the system. Signaling networks do not exist yet, so we used legacy radio technologies for the infrastructure. We determined how much energy the signaling and data networks would be using. This allowed us to calculate the energy consumption of a BCG2 network using the power profile, activation status, and load level from the live demo. The BCG2 demo is composed of three main components: the data network, the signaling network, and the controlling backend software. In addition, the demo uses specific software for user terminals, in our case a smartphone, and a graphical user interface that allows getting feedback from the system. The backend is the brain of the system. Its software receives signaling messages from the user equipment through the 3G network, which emulates the signaling infrastructure and uses the information to activate or deactivate the access points in the data network. The data network of small cells is emulated by a Wi-Fi system composed of a set of access points connected through an Ethernet distribution system. The signaling infrastructure is based on the 3G network available in the area of the demo and is used to feed the backend with information on the user terminals, such as their traffic requirements and their context information, like location. To localize users, we use an indoor localization system based on low-power wireless nodes distributed in the area of the demo.
Our graphical user interface allows us to easily follow the operation of the live demo. In this map of the area, it is possible to view the location of access points of the data network and the location of user terminals in real time. Individual meters monitor the energy consumption of each access point, and the global meter monitors the energy consumption of the data network. Each smartphone is running a user-selected application, which uses the 3G signaling network to provide the backend with context information and, when needed, the Wi-Fi data network to transmit and receive application data. A user who carries a smartphone and a localization device can move freely in the service area. The backend receives update on the user position and switches access points on and off according to user proximity. Other, more sophisticated algorithms can also be used. The status of each access point is shown in real time on the displayed map and with light bulbs attached to each access point. The energy consumption of each access point is directly related to its throughput, namely, the energy consumption increases as the data requests from the user application increase.
We are very excited about the potential of this new approach, which marks an important change in the architecture of next-generation mobile networks, the ability to dynamically tailor energy and resource consumption to real user needs. Using small cells with data and signaling separation can dramatically improve the energy efficiency of wireless networks and make the use of the communication resources and technologies much more flexible.